Here we're looking at maxima and minima. So let's just visualize what a max and a min look like. Probably something you're familiar with from algebra. A max might look like this, and a min could look like that. And we want to remember that the derivative of a function measures both slope of the tangent line and the rate of change at any instant or at any x value. So if we want to think about the slope of these, that's going to tell us the sign of the derivative of these. Remember, derivative is slope. So looking at this maximum and thinking about the slope, from left to right, this is rising. So it has a positive slope to start with. Then it has this soft peak. The derivative or slope at any soft peak is 0. So this, we're going to say f prime is 0. And then as we trace it left to right after that soft peak, it is falling. So it has a negative derivative. So for that max, it was increasing to 0 to decreasing. And then the min, if we trace it left to right, it's falling to start. So at first it's a negative derivative. And then it has a soft peak, so the derivative is 0 there. And after that, it is rising left to right as we trace it, right? We trace graphs the same way we read English, left to right. If it's going up, that means a positive slope or a positive derivative. If it's going down, that means a negative slope or derivative. So the max is increasing to 0 to decreasing for the derivative, and the min was decreasing to 0 to increasing. And we're going to see if there's some sort of pattern that we can get down from this. So first, we're going to get a theorem that says if the derivative is positive, if the derivative is bigger than 0, then what we know about the original function is that it's increasing. A positive derivative means a positive slope. Tells us that the graph is increasing, which can look a bunch of different ways, but maybe it's rising like a parabola, or it could be a flat line. But we know it's rising left to right if the derivative is positive. If the derivative is less than 0, meaning it's negative, then the original function must be decreasing or falling left to right. Lots of ways to draw something decreasing, but here's a couple. Just falling left to right. If the derivative is 0, instead of being positive or negative, then the original function could have a soft peak, right? We just talked about that. At a soft peak, the derivative is 0. Or it could be constant. It could be a flat part of the graph would have a derivative of 0. So it could be the top or bottom of a soft peak, or it could just be a flat, constant part of the graph. So to do this without a picture, determine where the function is increasing or decreasing, we would have two steps. The first step is to take the derivative and set it equal to 0, or figure out what makes it discontinuous, what makes you divide by 0 in the denominator of the derivative. And identify the open intervals determined by these values by doing step 2, testing a number before and after the critical number to see what the derivative is doing, or where the derivative is 0, we want to test a number before and after. So if 6 makes the derivative 0, you plug in f prime of 6 and you get out 0, you want to test a number before 6, like maybe 5, and a number after 6, like maybe 7. And then determine what's happening with the derivative before and after. So if you plug into a derivative, a test value, and the derivative is positive, it's bigger than 0, then the original function is increasing. If you plug into the derivative and you get a negative out, remember that means the original function is decreasing. And from that we get a definition that a critical number of a function is an x value in the domain of f such that the derivative is 0 or undefined. So the critical number is whatever makes the derivative 0 or undefined. So let's look at this and find where this function is increasing and decreasing. So our first example of finding increasing and decreasing our function is x squared minus 11x. And we want to figure out the intervals where it's increasing and the intervals where it's decreasing by using these two steps from above. So the first step was to take the derivative and see where it's 0 or undefined. So our first step, we're going to take the derivative of this function and set it equal to 0. So the derivative of x squared is 2x. Derivative of negative 11x is negative 11, and we're going to set that equal to 0. Here we have a linear function. It's an mx plus b. So to get x by itself, we're just going to add 11 over. So we'd get 2x equals 11, and then we're going to divide by 2. So x equals 11 halves, and I can see if I can make that a decimal. So 11 divided by 2, if it gives me a decimal that doesn't terminate, it keeps going forever, then I'm going to have to leave it as a fraction. But 11 divided by 2 is just a nice 5.5. So I'm going to make it a decimal. That way I have an easier time picking a number that's smaller and bigger than that for my second step. Because our second step is to make a sign chart. So I'm going to put 5.5 on here. This is the first number that goes on here. This is called the critical number. It makes the derivative 0. So here is my critical number. X is 5.5. And then I can test any number before and after that one. So before 5.5, I could test 0. And remember, I want to know the sign of the derivative because only the sign of the derivative tells me whether I'm increasing or decreasing. So I never want to plug into the original on a sign chart. So I'm going to plug into the derivative, which is 2x minus 11. So 2 times 0 minus 11 would give me 0 minus 11. That's going to give me a negative 11. And the number doesn't matter that you get out. It matters the sign. So we got a negative number out. So if we have a negative derivative before 5.5, does that mean that the original function is increasing or decreasing? It means we're decreasing. After 5.5, I can plug in anything that I want to. Maybe I'll plug in 10. Any number to the right of 5.5 will do. Always plug into the derivative, not the original. Only the sign of the derivative tells you increasing or decreasing. So 2 times 10 is 20. 20 minus 11 is definitely just going to be a positive number. So I go from decreasing to a 0 derivative to increasing. A positive derivative means increasing. So decreasing to 0 to increasing. And we can make a conclusion about relative max or min in a second. You might already know just by visualizing it. But for now, this problem only asks where are we increasing and where are we decreasing. So I want to write that in interval notation. So we have our critical number at 5.5. I want to figure out where are we increasing and where are we decreasing. Well, we are increasing after our critical number. So not 10 to infinity, but from our critical number on. So 5.5 to infinity. And then we're decreasing before our critical number. So not negative infinity to 0. 0 was a random test value. I could have just used 5 or 4. We're decreasing before our critical number. So negative infinity all the way up to 5.5. Just make sure you don't put any random test values in there. You would only switch increasing and decreasing at a critical number. And you can even write yourself a note if you feel like that's going to trip you up. And after this, we're going to look at what this looks like visually. But having a sign chart gives us a pretty good idea of what the graph looks like already. Just knowing where it's increasing, where it's decreasing, and where we have our critical number, where that soft peak would be.